So let's talk about observable in quantum mechanics. Like I meant observables like energy, position, momentum. What are the things?
In quantum mechanics, observables are physical quantities that we can measure, and each one corresponds to a Hermitian operator. So, energy is associated with the Hamiltonian operator, position is represented by the position operator, and momentum by the momentum operator. When you measure these, you get eigenvalues, essentially possible outcomes. The wave function state determines the probabilities of these outcomes. So, each observable is a tool for understanding different aspects of a quantum system.
So why not directly use those things?
Well, in the classical world, you can measure things like position or momentum directly. But in quantum mechanics, it's more subtle. These observables are tied to operators acting on wave functions, and measurement outcomes are probabilistic. Don't have a value until you measure. The act of measuring collapses the wave function. So these operators and the how we handle the uncertainty and probabilities.
So tell me another observable that we observe in quantum physics, or like you mentioned about energy, position, momentum. Are any other things?
Absolutely. Another classic observable angular momentum, both orbital and spin. In fact, spin is purely quantum mechanical and doesn't have a classical counterpart. You also have things like parity, which relates to symmetry, and even more complex observables like the Hamiltonian of different interactions or the number operator for counting particles in certain systems.
How how did these observables are related with the wave function of the particle?
Each observable corresponds to an operator that acts on the wave function. When you measure an observable, the wave function collapses into one of that operator's eigenstates. The eigenvalues are the possible outcomes of the measurement. The wave function's shape, its amplitude and phase, determines the probability of each outcome. So, in short, the wave function encodes all the statistical information about what results you can expect when you measure any observable.
Okay, how does this eigen operator eigenstate, like I need to understand this operator eigenstate, that what do you can you support this statement?
Sure. Imagine an operator as a mathematical machine that acts on a state. An eigenstate is a special input that this machine just scales. In other words, if you feed an eigenstate into an operator, you get the same state back multiplied by a number, the eigenvalue. When we measure an observable, the system collapses into one of these eigenstates, and the result you get is that eigenvalue. So eigenstates are the states where the observable has a value.
But first of all, who introduces these concepts of operator and these eigen eigenstate and the eigenvalue? How they think first that we can solve by this way?
The groundwork comes from the early days of quantum mechanics. Max Born and others realized that physical observables should be represented operators acting on states. Werner Heisenberg, with mechanics, and Erwin Schrödinger with wave mechanics both contributed work. The concept of
So can you please explain the question and the question again? So I asked like how did this operator eigenstate, eigen value, and this measurement process first, how they think to include so that they can get the uh, solution and they can help us to give the appropriate results.
In quantum mechanics, the big idea was that physical quantities like energy or momentum aren't just fixed numbers. They're represented by operators, which are mathematical tools that act on the wave function. Now, these operators have special states called eigenstates, where measuring that observable always gives a definite outcome, called an eigenvalue. When you measure, the wave function collapses into one of these eigenstates. This framework ensures that even though quantum outcomes are probabilistic, they still follow strict rules, allowing us to predict probabilities and understand the physical world in a logical way.
You have given some good intuition, but I ask like mathematically, what are the five postulates of quantum physics? How mathematically they thought that we should include in such a way that the result are given and we can measure one or two body quantum system in that way.
You're asking about the core mathematical foundations. The postulates guide everything. First, the state of a system is a vector in a complex Hilbert space. Second, observables are Hermitian operators acting on these states. Third, measurement outcomes are the eigenvalues of these operators. And after measurement, the state collapses into the corresponding eigenstate. Fourth, the time evolution of the state is governed by the Schrödinger equation. Fifth, for composite systems, the total Hilbert space is a tensor product of subsystems. These postulates ensure that quantum systems evolve predictably, measurements have well-defined probabilities, and even complex multibody systems can be described.
That is okay, but how did also the end result is also probabilistic. How can you defend this sentence?
Right. The postulates embrace probability because quantum systems are inherently uncertain. The wave function encodes all possible outcomes of a measurement, but you can't predict a single definite result, only the probability of each. When you measure, the wave function collapses into one of the eigenstates, and the outcome matches that eigenvalue. The probabilistic nature arises from the wave function's squared amplitude, which tells you the chance of each outcome. So the math gives structure, probabilities give reality.
How do we find the clue for the Heisenberg uncertainty relation from this core five postulate? Is there or not?
Yes, the Heisenberg uncertainty principle emerges directly from the postulates. Since observables are operators on a Hilbert space, the position and momentum operators, for example, do not commute. The commutation relation between them is tied to the uncertainty principle. Mathematically, the product of the uncertainties in position and momentum is bounded by a non-zero constant. This comes from the mathematical properties of operators and their commutators. So the uncertainty principle is a natural consequence of the core structure laid out by the postulates.
So what about this? So if A and B are two operator, if they commute, so we will get the system, or if they do not commute. So what does it means in language of uncertainty?
When two operators commute, meaning their commutator is zero, you can measure both observables simultaneously with perfect precision. There's no uncertainty trade-off. In contrast, if two operators don't commute, there's a fundamental limit on how precisely you can know both at once. This is exactly what the uncertainty principle quantifies. Non-commuting operators mean there's an intrinsic limit on how well you can know both quantities at the same time. More certainty in one means less in the other.
So here we have to follow that two operators should do not commute so that we can obey the uncertainty relation.
Exactly. The uncertainty relation arises precisely when operators don't commute. For example, position and momentum do not commute, which gives you the famous uncertainty principle between them. That's why we can't simultaneously know both with perfect precision. If two operators commute, no such trade-off exists. So, non-commutation is the key mathematical structure that ensures uncertainty relations hold true.
What is the clue that we understand Hilbert space directly from quantum postulates?
The clue comes right in the first postulate. It states that any quantum system state is represented by a vector in a Hilbert space. This space is a complete, complex vector space with an inner product. In other words, Hilbert space is the mathematical home for all possible states. Superpositions, probabilities, and measurement outcomes are all encoded in this structure. So the Hilbert space is central. It's where every state lives, evolves, and interacts with operators. The postulates naturally build everything on top of that space.
Okay, but how do we understand that inner product from the hydrogen atom perspective, something like that?
In the hydrogen atom, the wave function is like a vector in Hilbert space. The inner product is how we calculate probabilities. If you take the inner product of a state with itself, you get 1, meaning the wave function is normalized. If you take the inner product of one state with another, it tells you how much they overlap. In other words, the probability of transitioning between states. For the hydrogen atom, energy eigenstates, those neat orbitals, form a complete set. The inner product helps us compute how likely the electron is to be found in a particular state. So it's the mathematical backbone of quantum probabilities.
Okay, this is pretty interesting to know that the inner product play a very crucial role actually. So why they have actually introduced Hilbert space in the abstract notion of quantum mechanics.
They introduced Hilbert space because it gives a rigorous mathematical framework to handle all quantum states. In classical physics, you often have simple numbers, but quantum mechanics deals with states that can be superposed, evolve in time, and have probabilistic measurements. Hilbert space is a complete infinite dimensional space that can handle these complexities. It gives a consistent way to define states, inner products, operators, and observables. Without Hilbert space, it would be much harder to describe and predict how quantum systems behave.
Suppose if you are Hilbert, uh, how do you think so that you have how do you frame that Hilbert space from scratch in order to map the quantum physics?
If I were Hilbert, I'd start from a very general place. I think we need a space that can handle all possible states, even infinitely many. It must have a natural way to measure angles and lengths, hence an inner product. This will let us talk about orthogonality, like independent states, and lengths, like probabilities. Also, it must be complete, so limits of sequences of states still make sense. Quantum systems often evolve that way. Once that foundation is set, we can introduce linear operators to represent observables and rely on the structure to handle superpositions, measurements, and evolution. In short, I'd build a flexible, robust mathematical playground that matches the complexity of quantum systems.
So you will start with the general notion, how we will handle the states, and then how do we measure angle and length, so inner product, and then how we talk about independent states like orthogonality and lengths like probabilities. So quantum system often evolve. So once the foundation is set, and then we use linear operator to represent observable the structure to handle linear operator to represent observable and that rely on the structure to handle superposition measurements and evolution. Okay, that's a very fantastic approach.
I'm glad you found that helpful. It's all about building a logical scaffold, from the abstract structure, like states and angles, to tools like operators, and finally to predictions, like measurement outcomes. Once you have that framework, quantum mechanics becomes manageable, even if still weird. If more puzzles pop up, we can always dig deeper.
So make a conclusion from this chat.
In a nutshell, we've explored how the entire mathematical structure of quantum mechanics rests on a few core postulates. States live in Hilbert space, observables are operators, and measurements yield probabilistic outcomes tied to eigenvalues. The uncertainty principle naturally arises from non-commuting operators, and the inner product in Hilbert space is the glue for probabilities and orthogonality. In short, we have a consistent, elegant framework that allows us to understand and predict quantum phenomena, even if it challenges our classical intuition.
Okay, thank you.